Hello everyone, thank you for joining. I'm Marika Giulietti and I'm a PhD student at SISSA in Trieste. This talk will present you an ALMA perspective on a sample of radio bright, strongly lensed dusty star-forming galaxies. First of all, before starting, let me spend a few words about the general framework in which we are moving. Indeed, among the several models which have been proposed in the last year concerning galaxy formation and evolution, I will mainly focus on the so-called coevolutionary models, in particular in the in situ scenario. This model predicts that the processes at the early stages of galaxy formation are strictly related and coordinate in time. In a nutshell, at the beginning, in the first phases, there is plenty of gas available in the galaxy. This gas is enough to sustain a violent star formation, which goes on to an almost constant rate, producing new dust and metals, which causes an obscuration of the system. So, on the point of view of the host galaxy, the object will appear as a far infrared submillimeter bright source, while on the point of view of the black hole, which is accreting material itself, gas itself, it will appear in the X-ray band as a faint nucleus. So progressively, the black hole accretion goes on and the nuclear power increases exponentially, overwhelming the star formation one. Therefore, at a certain point, when it will be bigger with respect to the star formation, eventually the quenching of the star formation will happen in a time which goes with several 10 to the 8 years. The interstellar medium is cleaned out and the object will appear as a bright optical quasar and will continue its evolution as a red and dead spheroid. So if we want to study this interplay between these two phenomena, the best target is the so-called dusty star-forming galaxies at high redshifts. Indeed, the dusty star-forming galaxies are thought to be the progenitors of the early type passive galaxy we see in the local universe. They are abundant at high redshift and they constitute the bulk of the star formation history up to redshift 6. However, there is an issue, which is the fact that dusty star forming galaxies are at high redshift are very compact and hard to resolve. But a way to overcome this problem is to exploit the features of the gravitational lensing. Indeed, the lensing, a source subjected to strong lensing, has its apparent luminosity increases together with its sizes, which appear stretched. A good strategy to select these events, which are very rare, is to rely on submillimeter surveys. In general, submillimeter offers several advantages. On one hand, because of the negative K correction. On the other, because there is almost a negligible or a totally absent contamination coming from the foreground object when regarding in general the lensing phenomena. And this offers advantages in the source reconstruction. Moreover, both model and observation predicts a drop in the number counts of the unlensed objects above a certain flux density threshold, which corresponds to 100 millijansky at 500 micron. Therefore, thanks to lensing, we have the opportunity to study the morphological details and the dynamics of regions inside these galaxies down to sub-kiloparsec scales. We will focus in particular in the Herschel Atlas surveys, which is the widest area survey undertaken by Herschel, also covered by 5 far infrared to 6 millimeter bands of Herschel, and also a variety of photometric and spectroscopic surveys from the optical to the radio. In particular, we will start from a sample of 80 candidate strongly lensed galaxies drawn from this survey and described in the work of Negrello et al. 2017. These sources spans a wide range of redshift from 1 to 4.5 and appears very bright in the infrared bands. Indeed, their total infrared luminosity, uncorrected for lensing magnification, are comparable with the one coming from the hyperluminous infrared galaxies. Up to the date, only 21 of these objects are confirmed to be lensed. For the remaining candidates, we still are waiting for higher resolution observation both in the near infrared and in the submillimeter, and also spectroscopic redshift measurements. A good indicator, a good tracer of both the star formation and the AGN activity is the radio emission. For this reason, in my work, which you can find here below, we reconstructed the far infrared radio correlation for starting from the sample of Negrello et al. In order to do so, we performed a cross match with the available data in literature and the first survey at 1.4 gigahertz, which covers the H-Atlas survey, and dedicated ATCA follow-ups for the southern fields sources at 2.1 gigahertz. This led us to a total of 28 counterparts. In particular, when performing counterpart association, an extremely important role was played by ALMA data. Indeed, it is essential to reconstruct this relation to correctly associate the radio emission with the submillimeter far infrared one. And since these objects are detected by Herschel, we know that it suffers of a really poor angular resolution. Therefore, we exploited the available data in the public data in the ALMA Science Archive and tried to give the most reliable association. As you can see in the images, there are several matches. The first two sources are still unclear, and also the ALMA data are indeed, the resolution is still not enough to discover the morphology of the sources, while the other one are still, you can find them in the literature, are still have been already modeled, and also ALMA data shows the lensed morphology. But still, we are waiting for more data for the remaining objects, and in this sense, ALMA can really make the difference. So as a result, we computed the Q-far infrared parameter, which is the ratio between the infrared luminosity, the far infrared luminosity, and the res frame radio luminosity. We found a slightly decline with the redshift, which is also comparable with what is expected in literature, and also found some excess in the radio, in particular for a few objects at a redshift higher than 2, which is a signature of the possible presence of an IGN. We compare our sample with the one from these works from Stacy et al., which is a sample of radio-selected lensed quasars, which are divided in unconfirmed, star-forming, and jetted sources according to the origin of their radio emission. We can see that our sample is in good agreement and follow the same decline as the stasis one with respect to the res frame radioluminosity. And we also tried to give a possible physical interpretation of this behavior, always in the framework of the in situ scenario. In particular, the first phases of the galaxies, since are characterized by the predominant effect of the star formation, we expect the radio emission to be mostly associated with the star formation. Therefore, the equifarinfrared parameters are quite high, reaching values of 2.5, and slightly declines as the radio power becomes more and more predominant, even reaching values lower than 1.8 when the radio emission mostly comes totally from the IGN, in particular in the jets. As you can see, the black line represents the evolutionary track predicted by the model of a radio loud AGN. So the model and the data are a really good agreement, and therefore we can say that this could be a possible physical interpretation of the behavior of the infrared parameter according to an evolutionary picture. However, still we are missing, we would like to confirm and to see in the details of those sources inside our sample which still remains unconfirmed, so we don't know still if they are lensed or not. In this sense, ALMA can really make the difference on one hand by unveil the real nature of these sources. Indeed, with its excellent high resolution will be extremely easy for ALMA to identify some lensed morphologies, but also as has been also proved in the last years in several works, to identify the dust and gas properties associated both with the star formation and also to trace the nuclear feeding and the dynamics of the feedback processes. As an example, I reported here one source in our which is among our sample of 28 radio counterparts, which is confirmed to be lensed and has been modeled extensively in literature, in particular in this work by Massard et al. 2018. ALMA data were used to model and perform source brightness, the pixelated surface brightness of the source, and reconstruct its original morphology, together with both continuum and CO spectroscopic data. Coupling this with Chandra X-ray observation, it was possible to identify the presence of an hidden AGN. Therefore, will be extremely important to perform such analysis for all the remaining objects in the sample. And also will be crucial to test the in situ scenario in general, the evolutionary scenario of galaxies. So I leave you here with my conclusions. In a nutshell, take-home messages are that ALMA already helped us a lot in unveiling, reconstructing the general properties of this sample, but still we are waiting for more data, and there is still a lot of work to do to complete not only this sample but the general view of dusty star-forming galaxies. I leave you here with the paper in which you can find all the things I have discussed in this talk, and also my contact, my email, if you want to talk about anything related to my work and also the talk, please feel free to contact me. So I end up here, and thank you again for following my talk.